Okay, so first I'd like to thank the organizers for giving me the opportunity to come and present this work, which was initiated when I was at Bicocca with the group there. It's a pleasure to be here in person, finally. And I would like to highlight the contribution of the student there at Bicocca, Davide Laudicina, who's online in the audience, who contributed most of the analysis, which will be presented in this work. And I'll be talking about meson screening masses at high temperatures, and in particular, I'll be talking about bridging temperatures from the order of the QCD phase transition all the way up to a very large temperature regime approaching or up to the temperature of the electroweak phase transition. So here's the overview of my talk. I'll give a very brief introduction, and in the first part of the talk, I will discuss the strategy to reach very large temperatures in our Lattice QCD simulations. In particular, I'll discuss how we fix the lines of constant physics, and also some short discussion of finite volume effects on correlation functions at finite temperature. And in the second part of the talk, I'll discuss the numerical results, our lattice setup, some discussion of our control over the systematic effects due to the finite volume and the continuum limit before presenting the final results of the temperature dependence of the screening masses before concluding. So screening masses, as you know, characterize the length scales of spatial correlations at finite temperature. And in particular, they parameterize the exponential decay of the correlation functions at large distances. They're interesting quantities because degeneracies in the spectrum of screening masses can tell us something about global symmetries and their restoration. And of course, 2-point functions in general are of phenomenological interest, both for meson operators and also for singlet operators as well. Of course, they're related through the underlying spectral densities to real-time quantities. In particular, for the lattice, screening masses are good observables because, and quite simple to calculate some of the simplest quantities we can compute. They're static quantities, so they aren't dynamic or real-time themselves. They're RGI, they're scheme and scale independent, so they don't require any complicated renormalization. For the operators, I'll be discussing the non-singlet operators. We can compute these correlation functions with a very good statistical precision, and there also exist computations of these observables through effective field theories, for which we can compare. So I'll be discussing computing these on a Euclidean space-time lattice, of course, and in general, I will consider a lattice of spatial dimension L and temporal dimension L0, which is inversely related to the temperature of the system. And generally, of course, we want to take the thermodynamic limit, or we want to be in the limit where the spatial size of the lattice is much larger than the fixed temperature. So the goal of this work is to compute these screening masses in a new regime of temperature up to and beyond 100 GeV using Lattice QCD. And of course, these screening masses do have a long and also more recent history in Lattice QCD. So what's the main challenge in lattice computations at extremely large temperature scales, much larger than the typical hadronic scale? And the challenge is actually to set the scale at very large, very large temperatures. So usually we're used to setting the scale using a hadronic quantity such as a hadron mass, and in our usual hadronic renormalization scheme, we set the mass of some meson or baryon to the experimental one in order to determine the lattice scale. And of course, in order to be in the scaling regime, the length scale associated to this typical quantity should be much larger than the lattice spacing, but much smaller than the volume or the lattice size. But at very high temperatures, of course, there's a new scale gets introduced, which is the temperature. And in order to be free of those systematic effects, we should also satisfy a similar scale hierarchy where the inverse temperature is much larger than the lattice spacing and smaller than the physical volume. But if we want to use a hadronic renormalization scheme to set the scale at large temperatures, then we have to satisfy both of these both of these conditions, and we end up with a double scale hierarchy if the temperature is much larger than the typical hadronic scale given by this mass. And of course, the way out of such a scale setting problem has been known for a very long time, and it's to use non-hadronic quantities such as a renormalized coupling to set the scale. For example, this finite volume coupling, the Schrodinger functional coupling, which depends, so where the renormalization scale is set by the lattice volume. So this condition here. And in particular, in the incarnation of this, we will set the renormalization scale by the inverse temporal size of the lattice. So the picture here, which is kind of illustrated using how to use a finite volume renormalized coupling to set the scale is in the hadronic world, we make contact with hadronic observable, for example, at very low temperatures where the size of the lattice is large. Then we can, at fixed bare coupling, we can decrease the renormalized coupling by changing the lattice size. And then we take the continuum limit by keeping the renormalized coupling constant and changing our bare parameters or lattice size. And this is the condition which fixes the line of constant physics. And we can iterate this process without reference to the hadronic scale here at low temperatures, and we can reach arbitrarily large temperatures or high scales. And this scheme in particular to reach large temperatures has been previously used in the quench theory, but in this talk I'll discuss the application to QCD. So just again, in a little bit more detail about the implementation of this step scaling procedure in order to set the scale or the temperature. Once we fix the coupling, the renormalized coupling at a particular scale, at some low scale, we can use a hadronic scheme to connect this to the physical temperature. And then, as you see in this plot, by decreasing the renormalized coupling in a certain way, we associate each renormalized coupling to a fixed temperature in physical units. And in this way, we can span a temperature range from a few GeV up to arbitrarily large scales or temperatures. Finally, so in order to set the line of constant physics, of course, we need to know the bare parameters which enter in our simulation. And to do this, we use the results for each lattice resolution. We interpolate the renormalized coupling in terms of the bare coupling, and this allows us to decide which bare coupling corresponds to the associated renormalized coupling for a given L0 over A. And to do this, of course, we're making use in this framework of the results for the non-perturbative step scaling or running of the coupling from the Alpha collaboration, who did this exercise for NF equals 3 quarks. And similarly, in order to extract the bare parameters, we use the data from the Alpha collaboration in order to compute the relevant bare parameters. So just to summarize, our line of constant physics will be fixed then by a fixed temporal extent, which corresponds to a fixed temperature and a fixed quark mass in particular, we'll be talking about the chiral limit, where at 0 quark mass. And for each temperature, then what we do is we keep the number of, or the lattice resolution on the spatial lattice fixed. And eventually this means that when we go to very large temperatures, we will end up with a small physical volume, a small volume in physical units. So the next question which arises is, of course, when we arrive at very large temperatures, we arrive at very small physical volumes, so much smaller than the typical hadronic scale, so much smaller than 1 Fermi, for example. And typically, of course, this is a bit counterintuitive that we're allowed to do this. And in this example, where I'll be discussing the thermal screening correlators, one can systematically show that the finite volume effects are going to be sufficiently small when on these quantities. So here I define the finite volume effect on the spatial correlator as the difference between the finite volume correlator and the correlator where we make the world volume very large in one direction. And by performing a spectral decomposition in this direction where the volume is large, one can show that in fact the finite volume effect is given by this formula here in terms of an infinite volume quantity, this matrix element G sub n, and the leading finite volume effect is exponential in L times this energy En here. And the crucial ingredient here is that this En, which takes information from, I suppose, the high energy effective field theory, is that we know that at very high temperatures, we're guaranteed that the theory has a mass gap. So the energy that multiplies L in this exponent is positive, and in fact, it's known to be parametrically like G squared T. So this means that the finite volume effects on these correlation functions are exponentially suppressed in what's essentially the aspect ratio. And in our computations, this will be on the order of at least 20 to 50, so that we're guaranteed to be in the situation where, because the theory has a mass gap at large temperatures and our spatial volumes are much larger, so parametrically larger than this mass gap, we're guaranteed to be safe, even though we're operating in small physical volumes, to be free of finite volume effects. Okay, so this brings me to the second part of the talk. And on this slide, I want to emphasize some details of our lattice simulation. So we're operating the chiral limits with three quarks. We, in the end, cover this wide temperature range, which is just illustrated in this table, with temperatures going from 1 to 160 GeV. We use order A improved Wilson fermions, either two formulations with, depending on the temperature. And we have 4 lattice resolutions in the temporal direction between 4 and 10, so rather wide handle on the lattice spacing over a factor of 2. And here you can see just to give you an idea, for each of the lattice spacings, so the resolutions here, I have the Baire coupling, the parameters, and the improvement coefficient, just to visualize how many different parameters we scan. We have an extremely large spatial lattice size, which, as I said before, gives rise to this very large aspect ratio. Because we're at extremely physically large temperatures, we already heard that the topological susceptibility falls extremely quickly. So we operate in this sector of fixed topological charge. And one final detail is that we use shifted boundary conditions, which aren't particularly relevant for this work, but help with certain renormalization problems for other quantities. So the exact correlation functions that we'll study are in the flavor non-singlet sector and static correlators, so projected to zero Matsubara mode. And we'll look at correlation functions of the following densities, so the pseudoscalar and scalar density, and the 2 currents, the vector and axial currents. Because we're looking at non-singlet correlators, there's only the quark connected contribution. And here in this plot, and in general, later on, what I'll show is results from the pseudoscalar sector and also for the vector current correlator. So on the top plot here, I have the correlation function for the pseudoscalar operator at some very large temperature, and on the bottom plot for the vector correlator. And you see in both cases a very, very good and clean signal, which we'll describe more in the following slides. There's one further detail which arises at these very large temperatures in large volumes, and that is related to the fact that the Dirac operator has a large gap in physical units, which corresponds to the lowest fermionic Matsubara mode. And this means that the propagator essentially at large spatial volumes compared, so at large distances compared to this inverse temperature scale, the propagator becomes very, very small. And this means, of course, that usually in lattice QCD, when we solve the Dirac equation using an iterative method and a global stopping criterion, that the accuracy on the solution at very large source sink separations or very large distances can become very low. So that's illustrated here. The blue points you can see, instead of the expected exponential decay, you get some weird behavior out here. But this is cured using a trick called distance preconditioning, where you essentially pre and post multiply the Dirac operator by a known function, which means that the solution vector, all components of the solution vector after this preconditioning have a similar magnitude. And after this, you get a very clean signal to very large distances. And you can see that the correlation function here really is suppressed over many, many orders of magnitude. Yeah. Okay, so the observable that we're computing, of course, eventually is the screening mass. So we use a particular definition of the effective mass here. And here in the top plot, I show the effective mass for the pseudoscalar operator at some large temperature of 30 JeV. And in the bottom plot for the vector correlator, and you can see so in units of 2 pi t, which is the leading order prediction for these masses. And you can see that there's a very clean signal, and also in the vector channel, there's essentially no signal to noise ratio problem, and that's because the splitting between the pseudoscalar and vector channels is very small at large temperature. So from these effective masses, we can extract very precise results, and of course that means that we have to have good control over our systematics. Because we also want them to be of high accuracy. So you can see that excited state contamination is not a significant problem because we can go to such large distances. And in the next 2 slides, I'll discuss how we control the finite volume effects and also the continuum limits. So as I explained earlier, finite volume effects are expected to be very small on general grounds on these correlation functions. And indeed, we checked explicitly that by changing the volume in the directions transverse to the correlation function, keeping, of course, the temperature fixed, changing the volume by factor 2 or 3, we get very good agreement, actually, as expected on the effective mass. So here, the red points are in the large volume, and the blue points are in a volume which is smaller by a factor 3 in the transverse directions, and you see essentially no effect either in the pseudoscalar or vector channels. Then, of course, we need to perform the continuum limits. And before we do that, for each L0 over A, so for each lattice resolution, we subtract the leading order lattice artifact, which is convenience. So you subtract from the mass the difference between the lattice and continuum correlators at leading order in perturbation theory. And so here on the right hand, so here on the right-hand plot, I show the pseudoscalar mass in units of 2 pi t for all the temperatures spanning the range from 160 GeV down to 100, so down to 1 GeV. These are all displaced, of course, otherwise they'd be all much closer to 1. And you can see here, we're doing an extrapolation in A over L squared, so in A squared, because these are order improved quantities. And you can see we have a very good handle on the continuum limit. So we span more than a factor of 2 in the lattice spacing. And we've also checked that using Ansätze with cubic or even log terms give good agreement. So on the next slide, the blue points you see here, the same for the vector mass. And you can see again, we have very good control over the continuum limit, and just the statistical error increases a little bit for the lower temperatures. One more remark on chiral symmetry restoration. Of course, as I mentioned, from the spectrum one can also probe the restoration of flavor symmetries. And of course, classically, under singlet transformations, the pseudoscalar and scalar operators are connected, and under the non-singlet chiral transformations, the vector and axial vector are related. And what we see here in the data in the top panel in blue is the pseudoscalar effective mass for, I can't actually remember which temperature this is. I think, sorry, I'm not sure exactly which temperature it is, and the scalar, and you see that there's actually zero difference between the points. They really lie on top of each other, and the same is true for the vector and axial vector. So we basically observe for the whole temperature range, I mean, from 1 GeV higher, that there's excellent agreement, as we of course all expect. There's no remnant of either anomalous or chiral symmetry breaking. Okay, so this brings me to the final temperature dependence of the screening masses. And what we observe is that there's a very smooth dependence on the temperature, basically on the inverse log of the temperature, which is of course related to the coupling. And this leads us to make the choice to parameterize the temperature dependence in terms of this function g hat squared, which you'll recognize is basically the two-loop coupling. But this is just a choice. I mean, for us, it's just a way to parameterize the results. As a function of the temperature, we're not introducing any perturbative approximation here. So on the y-axis here, I show the masses as a function of this this function of the temperature. For the pseudoscalar, we see this approach, so a crossing from one, an increase, and then bending over. And in the vector channel is in blue, this kind of monotonic behavior towards the tree level value. There is a prediction at NLO, of course, as well, and that's shown in the dashed line. And at this, and where we interpret now the g hat squared as the coupling in this approximation. So the first features of these results are that there's only a few % deviation from either the tree level value or the NLO results. We see a significant splitting between the pseudoscalar and vector channels at all temperatures. So the lowest temperature here, the rightmost point corresponds to 1 GeV, and the leftmost point here corresponds to more than 100 GeV. And thirdly, we see also a correction which is the same sign. So it's more. So we see the data here are all greater than 1. So we see that the correction has the same sign as the NLO. So then finally, we can introduce a parameterization, which a polynomial parameterization in terms of this function g hat squared, and these are shown as the bands, the red and blue bands. And what we see is that for the pseudoscalar, the contribution of so firstly, I should say that if we leave these first two parameters free, we see agreement with the leading order and next to leading order prediction. Then they can be fixed to those consistently. The third order piece is very small, And so really what's left over is the fourth, the pieces multiplying the fourth order. We see that for the pseudoscalar, this contribution is negative, and it actually cancels the quadratic contribution at about 1 GeV. So you're left over with something which is consistent with the leading order prediction. And the vector, in the vector channel, you receive basically a large contribution at 1 GeV, which must be due to the spin dependent interactions. So it's the same order as the NLO correction. So another way to visualize the same results are on the top panel. I show the difference of the pseudoscalar mass in units of 2 pi t subtracted of the NLO results. So the difference with the NLO results, and you see this very striking behavior, this very linear behavior when it's plotted as a function of g to the 4. So that's just visualizing that essentially the difference is very consistent with g to the 4 scaling, and it's also significantly different from 0 so we see a significant deviation from the leading order all the way up to this extremely high temperature scales of 160 GeV. And finally, then another way to plot the result for the vector is to look at the vector minus pseudoscalar splitting. And again, you see this is consistent with g to the 4 scaling. So it's linear on this g to the 4 scaling. And it's also significantly different from 0 at all temperatures. Okay, so I think I should move on swiftly to my conclusions, which are that we've performed some, and we've accumulated some results from QCD up to these very, very large temperature scales for the first time. And that's been possible using a scale setting using a finite volume coupling. We validated the simulation strategy. The simulations are, in fact, in a sense, straightforward once the bare parameters are known. And we can obtain very precise results in some sectors, for example, for non-singlet correlators. And I suppose what we see is that higher order corrections are certainly relevant even up to these astoundingly large temperatures where, yeah, I mean, in the three flavor theory. So I think I'll leave it there, and thank you for your attention.
Thank you very much for this high temperature presentation. Are there questions or comments? Over, please. I come to you.
At these very high temperatures, you probably have a real plasma, so your coupling should be small, and then your meson would be a 2-quark or multi-particle state. So I'm wondering, in the fit function, you fitted cosh, right? So if you have a multi-particle situation, one would expect a power law modification. Have you tried that?
This is the screening. We're looking at the spatial correlators.
Yes. Same thing. So if you take, say, if you evaluate a meson, say a pion correlator on a free gas, then you would get a power law corrections.
That's certainly not the case, right? Because I mean, the coupling, well, I mean, firstly, the coupling it's not small at these temperatures, right? It's still 0.1, roughly. I mean, so alpha at the scale of, at the Z pole mass it's not 0. So I think that's, yeah, I mean, I don't think we're in the case where, I mean, the free theory is very particular, and I mean, really, I mean, as you know, that I mean, the running of the QCD coupling, I mean, you only get to the free theory at the Planck scale or something like this, right? I mean, still, it's extremely slow. Maybe I'm misinterpreting here.
The coupling is certainly not 0, but the question is whether you have a bound state or not. So if you don't have a bound state, if you have, say, a scattering state, at non-zero coupling, that's fine. But if the particles, if you have a scattering state, then you would have a cut rather than a pole in momentum space. And that introduces power law modifications. So that's the background of the question.
Okay, so yeah, certainly in the temporal correlator, okay, I need to think about it for the spatial correlator. But I mean, you see this, I mean, this is, I mean, here I can show you the correlation function, right? And it's decaying exponentially. This is certainly not a power law.
I think we leave it for a private discussion tomorrow. Are there other questions? Yes.
When you showed the temperature dependence and E and the V were not degenerate, and you showed first one, which it goes to one that was not a joint, this one, here here you just fit with this NLO form, right? I mean, is that?
Well, no, this, sorry, just to emphasize.
And no, let me then, exactly. Then coming to the next slide, then you talk about P0 and P1 fixing and then letting the others being the free parameter. So I was asking whether, I mean, perturbative predictions coming from above to the free limit, what is there is.
Sorry, say it again.
So this analysis, okay, when you say that you see that the like the spin dependent contribution and so on, the corrections are being of different sign in different channel. So this thing is kind of, is it a complementary information what perturbative theory has at this temperature, like channel dependent correction, or it's just perturbative theory also kind of find these corrections to be channel dependent? I mean, or you first of non-perturbatively find this? I mean,
so the only correction, there's only the leading, so there's only an NLO prediction, which is spin independent. So, yeah.
This at this high temperature being spin dependent correction is the first result.
As far as I know, it's the first observation of this and I mean, it's very striking that it's still there at large temperatures. Yeah.
Okay.
But as far as I know, there's no, I mean, there's no knowledge of this, of the spin splittings in this or higher orders, but maybe, yeah. Yeah.
Okay, I have two questions. The first one, do you have any problems with autocorrelations? Because if you decrease lattice spacing, I would probably expect that there will be some issues with it.
Not that we can measure. I mean, we do the best we can, of course, to measure them. But for this, I mean, you need long chains, and we've measured the autocorrelation times, and we see that they're small. But I mean, this is always a difficult problem, as you know.
Mm-hmm.
I mean, so there's one. I mean, of course, there's one observable which is particularly special, which is the topological charge, and this is the one I can tell you that. I mean, we're in a fixed topology sector, but physically that's also not a problem, because anyway, the topological susceptibility is surely extremely small at these temperatures. As we already heard, it decays like a very strong power of the temperature.
Okay, thank you. And the second question is, you're doing simulations in the chiral limit. I guess that's possible because you have very large temperature, but
yeah.
And if I understand correctly, you are also using Wilson fermions. So how do you tune then the quark mass? So is there a normalized quark mass which is 0, and then
the PCIC mass? Yeah.
Oh, yeah. Mm-hmm. Okay. Mm-hmm.
So I mean, okay, I didn't show, I mean, in terms of defining the line of constant physics, I didn't go into that much detail, but yeah, of course it needs to be kappa, I mean, you need to tune to kappa critical. But I think the details are in the appendix of the paper for this as well. It's essentially, yeah, okay. So it also relies on the same studies from essentially the same data as is used for the step scaling function from the alpha collaboration, in a sense. So they also need to tune to zero quark mass to because they're also operating in a massless scheme.
Okay, so let's
maybe
yes.
maybe Leonardo has a comment. I don't know.
Yes, go ahead.
Hi, I may add a comment on the correction. On the general ground, the spin-dependent correction are expected to be order G to the fourth. You know, if you just look the effective action, I mean, for the high temperature effective theory, you see that they are order G to the fourth. But you know, if you go instead, if you want to compute these masses beyond what has been done, or the G square, you realize immediately in the effective theory that you have terms which are non-perturbative. So you should solve the three-dimensional theory non-perturbatively to have a prediction in this slide here beyond G square. Okay. So on the general ground, you can say that spin-dependent terms are G to the fourth, but if you want to compute them in effective theory, you should solve also the effective theory non-perturbatively.
Make a comment? No. So we take it as a comment. I don't see any other questions. So thank you, Tim, another time. And we come to the next talk.